How do scientists determine if a new drug is more effective than a placebo? Or how does a marketing team know if one advertising campaign is truly generating more clicks than another? They often rely on a powerful statistical tool to make sense of the noise and find the signal. That tool is called ANOVA, or Analysis of Variance.
Think of it like this. First, we look at how spread out the data is inside each of these individual groups. This is the within-group variation. Then, we look at how much the averages of these groups differ from each other. This is the between-group variation. If the variation between the groups is much larger than the variation within the groups, we can be more confident that the differences we're seeing are real.
But what happens when our data isn't in neat, separate groups? What if our data looks more like this, where we're interested in the relationship between two continuous variables? This is where ANOVA for regression comes into play. It might seem different, but the core idea of partitioning variance is exactly the same. To understand ANOVA in regression, we need to look at three key distances for each data point. First, we have the total distance, which is the difference between our actual data point and the overall average of all the data points. This represents the total variation of that point from the mean. Next, we have the residual, or the error. This is the distance between our actual data point and the value our model predicted. It's what the model couldn't explain. Finally, we have the regression distance. This is the variation that our model did explain. Notice something interesting? The total distance is the sum of the residual and the regression distances. This isn't a coincidence, and it's the key to understanding ANOVA for regression.
Now, let's take this one step further. What happens if we square each of these distances for every single data point? Each of these squared quantities generate a geometrical square with an area representing the squared quantity. Then we stack up all the squares obtained for each category. The next step is to add up the squares of each group of squares to obtain SST squares, SSE squares, and SSR squares. If we sum up all the squared total distances, we get what's called the total sum of squares, or SST. This represents the total variability in our data. If we sum up all the squared residual distances, we get the total error sum of squares, or SSE. This is the total unexplained variation, or error. And finally, if we sum up all the squared regression distances, we get the total regression sum of squares, or SSR. This is the total variation explained by our regression model. And here's the magic. The total sum of squares is equal to the regression sum of squares plus the error sum of squares. SST equals SSR plus SSE. This isn't just a neat trick, it's the fundamental principle of ANOVA for regression.
But how can we be sure this is always true? Let's quickly walk through the mathematical proof. We start with the total sum of squares, SST. Now let's perform some clever algebraic manipulation. We can rewrite each observation as the sum of the residual and the fitted value. When we expand this expression, we get three terms: the sum of squared residuals, the sum of squared fitted values, and a cross-product term. This cross-product term is the key to our proof. We need to show that it equals 0. Why does the cross-product equal 0? The key insight is the orthogonality property of least squares regression. The residuals are orthogonal to the fitted values. This means the sum of the product of residuals and fitted values equals 0. This is a direct consequence of the normal equations in least squares. Step 1. We expand the cross-product term. We distribute the multiplication and separate the terms involving the mean. Step 2. We apply two key properties. First, the orthogonality property we just discussed. Second, the sum of residuals equals 0, which is another fundamental property of least squares. Step 3. We substitute these properties into our expression. Both terms become 0, proving our result. Therefore, the cross-product term equals 0, which completes our proof. This proves that the total sum of squares equals the sum of the regression sum of squares and the error sum of squares. SST equals SSE plus SSR. So to summarize, ANOVA in regression allows us to break down the total variation in our data into two parts: the variation explained by our model and the variation that's left unexplained. This decomposition is incredibly useful. A crucial application is in calculating the F-statistic. This statistic is essentially a ratio of the explained variance to the unexplained variance. A higher F-statistic suggests that our regression model is explaining a significant amount of the variation in the data, meaning it's a good fit. For instance, a marketing analyst can use this to determine if the money spent on advertising has a significant impact on sales. A high F-statistic and a low p-value would give them the confidence to say that the relationship is real and not just due to random chance. So the next time you hear about a statistically significant finding from a regression analysis, you'll know that the principles of ANOVA are working behind the scenes, helping us to separate the signal from the noise.
If this visual explanation helped you grasp the concept of ANOVA, subscribe for more similar content.